I'm just curious, how many of you have heard of NUMENTA or know what we're doing? Like a few of you. Are any of you members of our open source community or NUPIC? Aaron, I know that was a setup for you. Anyone else? No? Okay, great. So you may know that NUMENTA develops algorithms for machine intelligence. That's inspired by neuroscience and a lot of the new experimental data that's coming out of the field of neuroscience. But today I'm going to focus on one specific aspect of how we deploy our algorithms, which is analyzing streaming data. And specifically, I'm going to focus on detecting anomalies in streaming data. Okay, so here's what I'm going to talk about. A little bit about kind of generally about streaming analytics and anomaly detection in streaming data. Streaming analytics imposes some constraints and requirements that are quite different from what traditionally we expect in machine learning. So I'm going to try to articulate some of that from kind of our standpoint. Then I'm going to dive into how we use our technology, hierarchical temporal memory, for anomaly detection. And the technology has been designed for streaming data from the ground up. I'm then going to switch gears a little bit and talk a little bit generally about benchmarking. So it turns out because the application area has some constraints and requirements a little bit different, you have to think about benchmarking in a little bit different way too. And so we've created an open benchmark for detecting anomalies in streaming data. So I want to talk about that. It's pretty unique in what we've done. And then I'll summarize. So it's a somewhat algorithm-centric talk. There are a lot of excellent sessions, such as this week, on kind of software infrastructure and overall infrastructure for streaming data. But I feel like the focus on algorithms for streaming data has been really missing. And I think because of the unique requirements of the field, it's a little bit different. You have to think about it differently. So this talk is really going to focus a little bit more on the algorithm side of it. Okay. Okay, so real-time anomaly detection, as we all know, there's an exponential growth in Internet of Things, sensors, and real-time data collection systems. And this is driving an explosion of the availability of streaming data. I feel like the biggest application right now in this domain is anomaly detection for machine learning. Techniques like classification and clustering and so on do have their use cases, but anomaly detection gives you a very basic signal. Is there something wrong with my system? And everyone can use that. The other stuff is a little bit harder to productize and harder to take action on. So that's one of the reasons we focused on anomaly detection to begin with. There's literally dozens to hundreds of applications in this area. I've just listed a couple of them here. You may want to monitor your IT infrastructure, looking at your data center and your website, whatever, to see if there's something going wrong in your system. You might want to uncover fraudulent transactions. Monitor your energy consumption to see if there's something unusual there. You may want to track vehicles to see if there is some unusual movement in real time with your fleet of vehicles. Real-time health monitoring is becoming extremely popular, and certainly anomaly detection or detecting unusual things there is extremely important. So anomaly detection has hundreds of applications in the general context of Internet of Things and real-time data. But what's sometimes missed is that, so detection is good, detection is necessary, but often the real goal is prevention. You want to prevent something from happening. So take a look at sort of health monitoring as an example. Suppose you have a system that's monitoring your heart and the health of your heart in real time. It's great if it tells you, if it detects a heart attack and the fact that you're having a heart attack right now. But it would be far more valuable if it told me an hour ago that I might have a heart attack now. That's something I can really take action on. So detecting unusual behavior as early as possible, not just whether you detect it or not, is really critical in this area. Okay. Let's take an example. This is customer data that we work with. This is a large industrial machine, and it's showing the temperature of that machine over many months. As you can see, there's 3 dots here labeled with anomalies. This particular one is a very obvious one. This was a planned shutdown of the machine, and that's good. On the right-hand side is the one they were really concerned about. This was a catastrophic failure of the machine, and this was unpredicted, and it cost them hundreds of thousands of dollars with this very large system. And what's interesting is that the middle anomaly actually is the point at which the system started behaving abnormally. So you can see that there's a funny fluctuation there. It's a little hard for us to tell. It's somewhat subtle, but an expert in this area can tell, told us that was the point at which this thing started to go RE. And so that's, if they could have detected an anomaly at that point in time, it could have saved them a lot of trouble. Now, as you can see, a simple threshold-based system is not going to detect that. There's a very subtle kind of temporal signature to it. So this is the kind of thing that you see a lot of in Internet of Things. Okay, so let me set up the problem a little bit. So you have thousands and thousands of sensors and metrics in your system. For any given system, you have a stream of measurements at different points in time. So it goes back sort of essentially infinitely into past and is going to keep going in the future. That's kind of the streaming mentality. And you're at the current time t. And for anomaly detection, what you want to do is, given the past history of data, decide right now whether the behavior of the system is in some anomalous state. Okay? And then you have to report that decision, do any bookkeeping if you need to retrain your system. Everything has to be done before the next input arrives. Okay, so that's kind of the classic real-time setup. In particular for machine learning, not only do you have those constraints, but you can't look ahead. This is very different from the batch mentality. You can't look ahead in time. You have to make a real-time decision. There's no real training test set split. Every system has a unique behavior. You start your system and you go. And you have to learn online as you go along. So things like cross-validation and so on is much harder to do in this kind of setup. And the system must be completely automated and customized to each stream. Every single machine, I mean, even if it's the identical model, different deployments will start having very different behavior very quickly. So you need to really have customized models for each thing. But given that you don't really have a training set or test set split, it's challenging. So this is kind of the typical setup. So we've developed a technology called hierarchical temporal memory, or HTM. I'm not going to dive into the algorithm in too much detail, but it's an extremely powerful sequence memory algorithm that's derived from recent findings in experimental neuroscience. There's a lot of documentation and papers that we published around this. But just to kind of summarize the specific implementation, it's a very high capacity memory-based system. It models temporal sequences in your data. It's inherently a streaming algorithm. It has all of the properties that we want that I had in the previous slide. It's a continuously learning and continuously predicting system. Just like our brain is always predicting and always updating, so is our algorithm. There's really not much of a need to tune hyperparameters. It's very insensitive to most of the parameters. You can work across a very wide variety of data without having to tune things custom for every data set. It's a completely open source implementation, and you can go to github.com/NUMENTA, and there's tons of documentation about it. We have a pretty thriving open source community around this. So what I want to talk about is how we, one other thing about our HTM4 that's going to be important for the anomaly detection is that if you look at essentially what the HTM is doing, it's always trying to predict future inputs. Okay, so if you look at the current input to the system, it's a stream of data, x of t. Internally, the algorithm encodes this into a very sparse high-dimensional vector, a of x of t. And then it learns temporal sequences in the input stream and makes a prediction in the form of another very sparse vector, so pi of x. Okay, so pi at x of t represents a prediction for the next input, t plus 1. Okay, it's the exact same format of the vector. It's just predicting what it's going to see next. So here's a diagram of that. So when we apply it to anomaly detection, we do a couple of things with it. We have the input, we compute what we call a raw anomaly score, and then as the next step, we compute an anomaly likelihood measure. Okay? So if you look at the raw anomaly score, what this is it looks at the prediction from the previous time step, this x of t minus 1, the current input, and it computes a measure of how different the prediction is from the current input. Okay? So it's a measure of prediction error at this point in time. So this is normalized so that it's 0 if it was perfectly predicted and 1 if it was completely unpredicted. Okay, so this is an instantaneous measure of the anomaly, if you will. So you could actually threshold this and use this to report anomalies, but it turns out that in really noisy environments and really unpredicted environments like we see in typical deployments, we can actually do a little bit better by computing a likelihood score. So the likelihood score is a second order measure, whereas the anomaly score tells you whether something is unpredicted right now. The likelihood measure is a measure of how predictable the overall system is, and did that measure predictability change? Okay, so it's a kind of it's a higher order mechanism. And so what we do there is we first estimate the historical distribution of anomaly scores. So we're just using a Gaussian distribution. And then given a recent set of anomaly scores, we look at the tail probabilities of this distribution and try to see how likely is the current set of anomaly scores given the historical distribution of anomaly scores. Okay, and then we can detect an anomaly if the likelihood of the anomaly is really close to 1. Okay? So essentially we're modeling the predictability of the data as a Gaussian, and if you end up at the ends of that distribution, then you're very likely to be an anomaly. Okay? So just to summarize that part of it, HTM, the core algorithm, this is the heart of what's going on, learns temporal sequences. It continuously makes predictions, and it's a continuously learning system. The anomaly score tries to ask the question, was the current input predicted? Yes or no, a measure from 0 to 1. And then the anomaly likelihood is another measure on top of that, says, has the level of predictability in our system changed dramatically? Okay, and that's what we end up using. And later when we talk about benchmarks, I can quantify the difference, why we might need a likelihood score. Okay. Okay, so some results. So this is a few examples of detecting anomalies in an IT setting. This is from a product deployment. So this first example shows CPU usage on a server over time. And as you can see, there was a jump up in the middle, and the system detected that as an anomaly. But notice that in this case, I think it was a new software package that was deployed that had higher CPU usage. So it detects a jump as an anomaly, but now it's stabilized on a new normal, and so the anomalies quickly die away. And you're not continually reporting false positives. It's automatically adjusted to that. Another thing to note here is that there are unpredictable events in here, these little jumps, but that's normal for this system. So if you just look at the anomaly score by itself, you'd actually get a false positives all the way along here. But because of the way we use the likelihood score, this level of unpredictability is totally normal in here. Here's a second example of a load balancer. This is an extremely unpredictable stream. If you looked at load balancer latencies in a website, they're often pretty low, but quite often things spike up. And that's actually totally normal. But there was a case where there was a configuration mistake in the load balancer, and these high latency events happen much more frequently than normal. And so the system quickly detects that, can automatically detect that as abnormal as well. So this is an extremely unpredictable, completely different from this kind of stream. This is another example. This actually happened on our servers. This was a case, so we have our servers deployed on AWS, and there was a point in time when the AWS API servers on the East Coast shut down. And our system actually detected an anomaly an hour before the AWS API servers shut down. So what happened is that their API server started to get slower and slower, and our system, our server, started to fluctuate. The CPU usage started to fluctuate. And this was a very unusual temporal behavior, and our system automatically detected that as an anomaly, even though any particular value in there is totally normal. It's just that the behavior is one that hadn't been seen before. So we actually detected that an hour before it was reported on the AWS status board, which is kind of cool. So this product is called Grok. It's actually available by a company called GrokStream. So you can go to grokstream.com. They're a licensee of ours. So there's a commercial server-based product that detects anomalies in IT infrastructure. It can run thousands of anomaly detector models in real time. It takes approximately 10 milliseconds per input data to make a decision. And this includes the entire learning phase as well, because it's continuously updating. And there's no parameter tuning required. You don't really need to care about what type of machine or the characteristics. You can just start streaming the data and work. We've tried the system on many, many different types of data. Kind of a demo one that we use is looking at financial data. So this particular example shows a stock, ConocoPhillips, and what we're doing is monitoring stock price, stock volume, and the Twitter mentions for this stock over time. And you can see that right here, the Twitter volumes jumped, and actually a single spike is totally normal in Twitter. But what's unusual is kind of a sustained period of activity here. So it detects that as an anomaly, and the next, once the market opened, stock actually dropped, and there was a higher than normal, stock volume, amount of stock trading for that security. And it turns out if you dive in and look at the Twitter, it was because they had slashed the quarterly dividend. And in this case, Twitter actually picked this up and started talking about it long before the market opened and before the news was actually announced. So this is kind of shows the power of real-time anomaly detection in a streaming context. So this is an app called HTM for Stocks. It's a free demo application, real-time demo application. You can actually download it right now if you want on iOS App Store or the Google Play Store. This continually monitors the top 200 stocks, and then it sorts it by anomaly, so you can see which securities are in a most unusual state at any point in time.
What's HTM mean?
HTM is our acronym for hierarchical temporal memory, so that's the algorithm that thanks. And this is also fully open source. You can get all the code for this here, including all the model parameters and everything.
That Grok thing you just mentioned, is it also yours? Just commercial?
It's something that we've licensed to another company. Yeah. So it's it's theirs.
But it uses HTM?
That's also HTM. Yeah. Okay, so let me switch gears a little bit now and talk about benchmarking. So I've been showing you, isolated examples here and there of the system working, but how do you know it's really working? Can you quantitatively measure it's working? And in machine learning, that's important to do. It's not enough just to look at a few examples. You want to know, you want to have a little more rigorous benchmark of whether it's working or not. And it turns out for real-time anomaly detection, this was not easy. So evaluating streaming anomaly detection has its own set of constraints because the underlying application domain has its own set of constraints. And most existing benchmarks, and I'm talking specifically about anomaly detection now, are designed for batch data and not streaming data. And it's really, the other thing is we're interested in practical applications and practical deployments, not artificial data sets. So it's really hard to find anomaly detection benchmarks that contain real-world data that are labeled with actual anomalies. This basically doesn't exist. There's one benchmark out there that I know of other than ours, which is the Yahoo benchmark, but unfortunately that's not an open benchmark. It's only open to universities. So, but in theory, that data should be useful as well.
Have you taken a look at the benchmark on linear rule?
No, I haven't. I'd love to talk to you more, see if it meets this thing. So we saw there's a need for an open benchmark that's designed to test real-time anomaly detection, and we felt a standard community benchmark with real data could spur innovation in this field and help everyone. So that's what we created. And so we call it the NUMENTA anomaly benchmark. So this is NAB for short. It's a rigorous benchmark for anomaly detection in streaming applications. So there's basically two aspects to it. One is a real-world benchmark data set. So it has 365,000 data points from 58 streams. 47 of them are actually real-world data with real labeled anomalies. And we do have 11 artificial streams. So some of the examples I showed you earlier, like this one, comes from NAB. The second aspect is a scoring mechanism. We have a unique scoring mechanism that rewards early detection. So again, it's not sufficient to, it's good if you detect an anomaly, but it's even better if you detect an anomaly earlier. And then we also have different application profiles so you can trade off the cost of false positives versus false negatives here. So this is, NAB is a completely open resource. The repository is an AGPL licensed repository. It contains the data, there's source code for it, documentation, and you can go to github.com slash NUMENTA slash NAB to find it. We actually have an ongoing competition to expand NAB with more data because I feel we need an order of magnitude more data than this. So I'd love to see if there's more data we can incorporate in here. But let me talk a little bit about some of the details of NAB. Here's first a couple of examples of data files. This is an hourly service demand, and if you're used to working with this kind of data, it has a typical daily up-down kind of pattern. In this case, this is actually real-time taxi usage data in New York City. The New York City Metropolitan Authority makes this available to everyone. So you can see some examples of anomalies in here. So there's a spike in an anomaly here. This is actually the New York City Marathon. And if you look closely, there's actually funny patterns before that big spike. So usage was anomalous before you actually got that spike in demand. So in theory, you should be able to predict an anomaly before that spike occurs. Then there's unusually low demand. So it still goes up during the day, but it's much lower than normal. And that was Thanksgiving. You can see that it would be hard for a threshold-based system to detect that particular anomaly. So that's one example of the data files we have. This is a completely different one, again, in the IT domain. This is CPU. It's the server that's running these batch jobs. So it's sort of very spiky usage pattern. You can see here there's an anomaly where the spikiness suddenly becomes a lot more frequent. So this is a change in the system behavior at this point. But then this is the new normal. And so you don't want to keep getting false positives here, and then you get another spike anomaly at the end there. Okay, so you can see that the characteristics of all these data files are completely different from one to the other. But they're all sort of typical things you see in streaming data. So as I mentioned, one of the important things in NAB is how we score anomalies. So what we did is we created the concept of a perfect detector for streaming analytics. And we say the perfect detector would detect anomalies as soon as possible. The earlier, the better. You want to provide detections in real time. You want to have no false alarms if possible. You don't want to have parameter tuning. And you want to automatically adapt to changes in the statistics of the data. These are all characteristics of real applications in streaming data. So this is what we want to try to quantify in the benchmark. And the scoring methods used in traditional benchmarks don't really capture this stuff. So things like precision recall, they don't really incorporate the concept of early detection. So you need to modify. It's another dimension in your scoring. There's typically, because they're batch, there's an artificial separation of training and test sets. Well, if you want to do continuous learning, you don't want to stop learning when you're testing. You have to keep learning continuously. Batch data files allow look ahead, which is usually infeasible in streaming data, and they allow multiple passes through the data, hundreds or thousands sometimes for many typical algorithms, and usually that's infeasible in a real-time scenario. So how should we think about scoring? And here's an example, and you can think about, okay, where is the anomaly here, and where would you want to detect it? So this thing, there's a very obvious anomaly right at the bottom there where the system spikes down. But the actual problem actually happened well before that when the metric started going down. So ideally, you want to detect the anomaly here. But you don't really know where it is. So what NAB does is, so you have human labeled anomalies, in this case, let's say there. And what NAB does is puts these windows around each labeled anomaly. And what it says that you can detect an anomaly anywhere in the window that's a true positive. But the way the scoring function works is that you give higher score to earlier detections within that window. Okay, so it's okay to detect it right at that red point, but you will get a higher positive score if you detect it earlier in the window. And then if you detect it outside the window, it's considered a false positive and you get a negative score. Okay? So I'm not going to go into the detailed equations for this. We have a paper published on NAB that goes into all the detail for this. A couple of other points. There's application profiles which allow you to assign weights between false positives and false negatives and true positives. And you can imagine that different applications have different needs. So if you have an EKG example, let's say this heart attack example, then you're okay with a few false positives, but you really don't want a false negative, right? that would be really bad. On the other hand, if you look at IT and DevOps, those professionals completely hate false positives because it drives them nuts if their pager is always going off. And it's actually usually okay to have a few false negatives because their systems are designed with some inherent robustness in there. So exactly what the value of a false positive versus a false negative depends on the application. So in NAB, you can actually test with different weightings of that. And then NAB emulates some of the stuff I talked about earlier for real-time scenarios. So there's no look ahead allowed for the algorithm. You get one data point at a time, and you have to make your detection before you see the next data point. There's no separation between training and test files. Every stream is its own thing. So for every stream, you invoke a model, start feeding it data, and after a short period, you start counting the anomalies, and then you can do your scoring on it. And there's no batch parameter tuning allowed. It must be a fully automated system with a single set of parameters across all the data files. If you're going to do any parameter tuning, it must be done on the fly as you get the data. Okay, so again, this emulates real-world scenarios. But this is a very different mentality from typical machine learning, you can see. But that's what's needed in real-time scenarios. Okay, so you can test algorithms with NAB. We made it extremely easy to test, to plug in and test different algorithms. I'm going to show results with several different algorithms now. So we have the hierarchical temporal memory, which is the algorithm I described earlier. We have results from Etsy Skyline, which is a very popular open source anomaly detection technique. It has a mixture of statistical experts, and it's a continuously learning system. Twitter released an open source anomaly detection algorithm, I think last year. And it does a form of robust outlier statistics plus some temporal modeling as well. We have also Bayesian online change point detection, which is kind of a classic technique that estimates the distribution of your metric values and tries to see how different you are from that. And it's a very principled way of doing that. And this is a real-time version of that technique. So here are the results on all the files. So just look at this column for now. So the perfect detector, we scale the score, so the perfect detector gets 100. None of the algorithms are anywhere close to that right now. So the HTM does the best. I've split it out into two different types of runs. If you include the likelihood computation, you get a higher score than if you don't include the likelihood computation. So there's a significant difference between these two. And this is typically for the really noisy environments. That's where you see the extra benefit. After that, Twitter gets a score of 47, followed by Etsy. And the Bayesian change point detection is essentially at random. And this is because they make specific assumptions about the distribution of the data. And some of the data files meet it, but many of them don't. Where it does meet that assumption, it works really well. But the point is you don't know in advance. It's, I think you should, this algorithm could be expanded to do some mixture of distributions or a broader class of distributions. And it's something you can explore if you're developing these algorithms. Yeah.
Why do you try HTM with and without the likelihood?
This is just to see what the effect is of the likelihood, because we wanted to see if we felt the likelihood would help, but we didn't know for sure until we run this. So in production we always run it with likelihood. Yeah.
There's no undesirable computational burden.
No, it's very fast. So it's 10 milliseconds on my laptop per data record for everything. And then the other columns there show some of the variations if you look at different weightings of false positives and false negatives. I'm not going to go into that. So a couple of examples of runs here. So this is a CPU usage on a server. There's one anomaly here which all three algorithms get. So the diamond is the HTM, the square is Etsy Skyline, and the plus is Twitter in here. So all three get that. There's another smaller anomaly there, and this is a shift in the usage pattern. So Skyline and NUMENTA both get that. The red things are false positives. They're outside the window. So the HTM actually has some false positives outside of that window. And then Twitter does not detect the shift, but it gives a lot of false positives after that. So in this one, the Etsy Skyline actually did best because it detected both anomalies and there was no false positives and it was right on same time as everyone else. Here's an example of the machine temperature one, kind of zoomed in on that temporal anomaly. NUMENTA is the only one that, the HTM is the only one that really detects the purely temporal anomaly. Everyone detects the catastrophic failure, and then the HTM and Skyline actually have two false positives around here. Here's another IT server usage data. So there's a big spike up there, and Twitter and Etsy Skyline both detect that spike up, but the HTM actually detects it much earlier. And if you look closely, you can see there's actually a small shift in the usage. There's still a fair amount of noise in the data, and the shift is kind of within that noise, but there is a noticeable shift there. So if you can detect this temporal change, you can detect anomalies earlier. And this is extremely common in streaming data. You often see subtle signals in the data before the actual big catastrophic thing. Thank you. I mentioned the NAB competition, so here's a little bit more information on that. So we see NAB as a resource for the streaming analytics community. It's a completely open benchmark. We're at a 1.0 state, but I feel for 2.0, we really need a lot more data files with anomalies and more algorithms tested to really make it a much more valuable to the community. And so we have a NAB competition going on with cash prizes. You can either test additional algorithms and while meeting all the constraints of NAB and report them, or you can submit data files that have actual anomalies in this. And if you have access to data, I would highly urge you to submit this because it's extremely rare to get, it's very hard to get real world data with actual anomalies, and this would benefit the entire community in there. So we have cash prizes of $2,500 for algorithms and data. It's really easy to enter. It's not like we're going to get thousands of entries, so it's a pretty high likelihood of winning this. So definitely consider entering it. You can go to numenta.org/NAB for details. There's a deadline. I think it's by end of June or early July is the deadline for entering. So I hope you, some of you will consider that. It should be very easy to enter into this. Okay. So just to summarize, anomaly detection for real-time streaming analytics poses some unique constraints. So there's the very stringent real-time constraints and automation requirements. And the typical BATH methodologies do not really translate well into this domain. You really need to shift your thinking a little bit. I talked about HTM learning algorithms, which can be used to create a streaming anomaly detection technique system. It works very well across a wide range of data sets, at least the ones that we've tried. It's open source and commercially deployable. And then I discussed NAB, which is a completely open source benchmark for streaming anomaly detection. It includes a labeled data set with real world data, scoring methodology designed for practical real-time applications, and then we have a competition to expand the data set for future. And then here's some resources that you can go to. Most of these links I've already talked about. HTM Studio is a free desktop app that we're about to release that allows you to easily experiment with your data without sending it to the cloud or anything. You don't have to be a programmer. You can just download the app and try it. So if you're interested in that, please contact me and I can get you a link to that. It's in a private beta state right now. The other thing I want to point out is that our community has done many different versions of our code base and algorithms. In particular, I want to point out Apache Flink, which Iran Wright has been spearheading in our community. So he has done a complete port and a complete anomaly detection system using HTMs on Apache Flink. So I know from a deployment standpoint, that could be really interesting to some of you. And that's it. Thank you. Any more questions?
I was curious how HCM handles trending data. I'm not sure I saw any examples in the talk. So.
Yeah, so trending data is typically fine. What will happen is it's really if the way it trends really changes. So if it's sort of just a steady, gradual linear, it should be fine. But if it suddenly changes in the way it's trending, it'll cause a problem. We don't see that too much in streaming data, but it's definitely a possibility. If you look at like revenue, for example, that's going to be, that one might have an exponential. Yeah.
So it looks like the crucial point of your algorithm of HTM is figuring out the model and then detecting the likelihood of the anomaly as discrepancies between the model and the data. So is the model specific model for HTM, or do you have some generic kind of control for any kind of data, or do you allow different models?
Yeah, it's a generic model. So, sorry, repeat the question. Yeah. So the question is, we have the way our system works. We have a HTM model followed by the anomaly score and the likelihood. And the question is, how specific is that model to the data? So you have to define the number of input streams that's coming in, and after that, it's generic. So in all of the examples, and NAB actually is, you get a timestamp and a scalar value in the NAB data that I showed you. So once you know those two things, you can just instantiate it, and the parameters work across all of the different types of noise systems and patterns that I showed you. So you don't have to tune the parameters at all.
So the implication is that HTM data model is the best time series prediction model.
Yeah, it's hard to say it's the best, because for any specific thing, you can always optimize and tune for that. But it works very well across a very large category of data without fine tuning. And it's sort of interesting. I mean, I mentioned we're very inspired by the neuroscience data. There's a lot of findings in neuroscience and how you get a very flexible generic system like that. And so we kind of rely on that. It doesn't mean you'll be the very best at any particular thing, but you'll be very good at a wide range of things.
You mentioned that you use, I think, normal distribution and something like Gaussian. But do you construct, once you have the model, do you really construct the specific noise distribution for each data stream?
So the question is about the Gaussian distribution, and do we construct it specifically for every stream?
Do we construct other distributions?
Yeah, so that distribution is on, remember, it's a second order thing, so it's on the anomaly scores, not on the underlying data. So the underlying data can have any distribution. So the Gaussian is purely modeling the anomaly scores, and that, by looking at a large set of data, we've found that this Gaussian works pretty well for that. We don't have to tune it to specific things. But it's possible that other distributions, in some cases, could give better results. Any other?
In addition to that, you can detect the spike, meaning the extreme point.
Yes. So the question is, can we detect extreme, a single spike? And the answer is yes. If it's a very clean data, so you hardly ever see a spike, then a single spike will be very unusual. But if you get pretty spiky data, and spikiness is normal, then a single spike is not going to cause an anomaly. Okay, so a spike by itself does not mean anomaly. It's a spike in the context of past behavior, and it could or could not be an anomaly.
Suppose you are seeing analyzing, actually, they have given frequency of spike.
Yeah.
Your likelihood measure, the K, need to be adjusted as well. Meaning, you need to define how's the span of the interval that you want to.
Yeah. So the question is, if the frequency of the data changes, do we need to change the way we're doing the distribution? And the answer is no, because it's the underlying HTM model is modeling all of the temporal behavior of the system. So it's learning the common sequences. So if it's a lower frequency system, it'll have slower sequences. If it's a higher frequency system, it'll have higher sequences. So the likelihood is only on the output of that system. It's a little tricky. It's a second order thing. It's not actually modeling the data.
That memory, your HTM will keep a certain window of the sample.
Yeah. So the question about memory usage. The HCM system has a very high capacity memory for sequences, so it can remember things very far back in time. On the other hand, it will overwrite things that are where in the same context you have different behavior. It will very specifically override those things, and that's how it does its continuous learning. Any other questions?
Do these benchmarks perform well in the rule-based anomaly system as well?
Do these benchmarks perform well in rule-based? So the rule-based stuff that I'm familiar with is like from a simple setting a manual threshold or something like that. Those do not work well in practice. I don't know if you've used those, but you can set a threshold, and then of course, it's not just one system. You have hundreds of systems. You have to figure out what the right threshold is for everything. And then whenever there's any change, you suddenly start getting all sorts of false positives. It's not automatically adjusting, so you have to go back and retune it. So what happens in practice is that everyone turns those off. Or ignores them.
One more question. So on the learning, the captain memory actually purchase that somewhere, or the system captures and start learning from scratch, or can you use it?
Yeah, so the question is about kind of robustness and reliability and fault tolerance and stuff. So that's kind of a system level thing. So in some of the stuff we've showed, the systems do checkpoint. The stuff that Iran has done with Apache Flink is really cool because it can do that in a distributed setup and take advantage of all the reliability guarantees that Flink provides using this serialization. So I think it's a kind of a system level question that you can
Have you tried multi-signal? Meaning not just single. I have multiple.
Yes, so the question is, have we tried multiple data systems? We have, and actually our paper includes that, but it's even harder to get real-world data with multiple streams that are labeled with anomalies. I would love to expand NAB in that way.
Well, maybe the financial segment.
Potentially, yeah.
For the products coming into.
Yeah, that could be one example, that's right. Yeah. Okay.
To cut it short, but hopefully Subutai will be available afterwards. Just a super quick announcement from the organisers. The sponsors upstairs, fascinating, really smart people, really good to talk to, and they're feeling a little bit lonely, so if you feel like going and giving them a hug or whatever, give them some bags, that'd be great.
Where are the sponsors?
Oh, they are just in the top, sort of that corner of the building. So you go up the stairs and then towards the back, towards the street. Yeah, where the coffee and the drinks.
Okay, thank you.